This is the third part of the 10th module in our series on tensors. Specifically, these three videos deal with higher ranked tensors, rank 3 or higher. We're discussing how we can extrapolate the lessons we learned from the first 9 modules and predict or better understand how the mapping, the form, the structure, and the overall behavior of a tensor changes as its rank increases. And that could include either the contravariant or the covariant rank. Now, in the first two parts of this module, in the first two videos, 10a and 10b, we first introduced the 5 cases, which the base case is the rank 3 tensor, the bilinear map, and then we increase or decrease the covariant and contravariant ranks by 1 in order to generate the other 4 cases. And so far, we've looked at the input-output mapping, how that's affected by the rank, as well as its form and structure, and we left off with a slide that looks a lot like this. In this video, we're going to touch upon 3 more characteristics, one of them being the coordinate-based input-output relationship, another one being how to generate the tensor from the coordinate matrix and its basis, and the last one, probably being the most important one, is how to appropriately apply transformation of basis to this tensor. And then we'll also talk about the tensor product space. So the coordinate-based input-output mapping, what is this? We know that we can decompose any tensor down to some sort of coordinate matrix or array and its associated basis. We saw this with the primal vector, right? The primal vector could be decomposed into a basis set as well as a coordinate array, and we could do something similar for the covector as well as a linear map by linear form. And we can then also define relationships which ignore the basis and are only defined in terms of the coordinate arrays or the coordinate matrices. Now, we lose some flexibility when we do that, right? We either have to assume orthonormal standard basis, or we have to assume that the bases are already baked into the coordinate values themselves. Regardless, that's what we're talking about here, is the input-output relationship based on, well, that depends on coordinates only. So what we have, if we look at the base case, is 2 input coordinate arrays that are being multiplied again with respect to the appropriate contracted ranks, multiplied by this coordinate matrix. That's why there's no arrowhead up here. And then the basis correspond to the inputs and outputs. So we have one basis here, inverted basis that's associated with the first input, another basis here that's associated with the second input, and then one output basis that's associated with this over here. If we increase the covariant rank, we have one more input and we have one more inverted or dual basis set. If we increase the contravariant rank, the number of inputs stays the same, but we have now a new output primal vector which gets incorporated into our final result. And actually, I apologize, I made a mistake here. These are not vectors. We were just meant to present these in terms of coordinate arrays, but we can use the same expression. So now, instead of I misspoke earlier, I said in terms of only one output primal vector. Now we have it in terms of 2 column oriented coordinate arrays, and we combine those together into V pre-out. If we decrease the covariant rank, then we get rid of one of the inputs, and we also get rid of the basis that's associated with it. And if we decrease the contravariant rank, then we take what was previously an output and reduce it to a scalar, and that's only because this was contravariant rank 1 to begin with. And now you see that the basis that was associated with the output is now gone, and we're just left with the original 2 inputs. All right, so we observed from that an increase or decrease in covariant rank results in an increase or decrease in the number of dual bases associated with the coordinate matrix. Okay, we saw that, right? Up here, we have rank 3, and so there's 3, I don't know if you can see it anymore, 3 bases. Down here, we have rank 4, and so there's 4 bases, and then these 2 are rank 2, and so we have 2 bases and 2 bases. Now, if we increase or decrease covariant rank, that will affect the number of dual basis sets, which is also the inverted basis sets associated with the inputs. And if we increase or decrease the contravariant rank, it results in an increase or decrease in the number of primal basis sets associated with that coordinate matrix, and those match up to the outputs or the output arrays that are combined via tensor product to generate the output. I apologize, I probably shouldn't say vector here. This should be coordinate array. So we observe that the primal basis sets are taken directly from the output vector, or again, output coordinate array. And the dual basis sets are taken directly from the input vectors or the input coordinate arrays, and they need to be inverted. If you have questions about why the basis associated with the inputs are inverted and the basis associated with the outputs are not, you'll have to take a look back at either the linear maps module or the one on the rank 3 tensor. So what we see is that the number of primal bases associated with a coordinate matrix should match its contravariant rank, and the number of dual bases should match its covariant rank. And I know that I went back and forth a couple times using the term vector and array here. I apologize for that. But in this section, this slide and this slide, we're predominantly just talking about a coordinate matrix, as well as its associated input coordinate arrays, not vectors, and output coordinate arrays. All right, now let's take a look at a similar characteristic, which is how do we generate the tensor from the coordinate matrix as well as its basis. Now this equation should look familiar. We're going to use the summation-based form because as these tensors as their rank increases, it becomes more difficult to represent them otherwise. But you should be familiar with this type of expression. We used it for both the linear map, our brief explanation of the bilinear form, and then the more in-depth discussion of the bilinear map. And so there's some pretty predictable trends we can see here. So our original rank 3 tensor has a coordinate matrix with only 3 indices, makes sense. It has 3 bases, makes sense. And those same 3 bases are included here. What we're saying is that we can create our tensor through some product of the coordinate matrix and some basis set. Now all 3 of these should have the same form and structure. If this is an array, this should be an array, this should be an array. If this is a rectangular matrix, both of these should be rectangular matrices, or I should say that each element of the basis set will be a rectangular matrix. And so what we're going to see is that the form and structure of the tensor is reflected in the form and structure of the coordinate matrix, which is reflected in the form of structure of this product right here. Okay, so if we increase covariant rank, we add a new input, which requires a new inverted basis set, which is shown here when we're actually calculating the elements of our basis set, as well as over here where we're discussing with respect to what basis our coordinate matrix is defined. We need to add a subscript element that allows us to index the new rank, and then a summation to go along with it. If we increase the contravariant rank, we need to add a non-inverted primal basis set. Like up here, when we added a covariant rank, we need to add an inverted basis set, which we can imagine or visualize as a dual basis set. So we add this, its corresponding value here. Note that, in general, this should always agree with this, okay? Because we want to be taking the product of our coordinate matrix as well as its associated, one element of its associated basis set. So when we increase the contravariant rank, we need to add this superscript index here and its associated sum. When we decrease the covariant rank, we are going to get rid of the basis that's associated with that second input. We also get rid of its summation, and so that gives us what we see down here. We have For the linear map, we have a single input and a single output, so that leads us to a single inverted dual basis set, as well as a single non-inverted primal basis set, which is the same as we see right here. 2 indices, because this is only rank 2. And then going from here to down here, if we decrease the contravariant rank, right, we need to eliminate what was this element k up here. We need to eliminate the basis associated with the output, so that's gone. I think I forgot to get rid of it here. This definitely needs to go away. And so this leaves us with a covariant rank 2 object. So when we look at this equality, we observe that an increase or decrease in covariant rank results in an increase or decrease in the number of input-related sums. This also results in an increase or decrease in the number of dual basis sets, right, the inverted basis sets, associated with a coordinate matrix. An increase or decrease in contravariant rank results in an increase or decrease in the number of output-related sums. This also corresponds to an increase or decrease in the number of primal basis sets associated with our coordinate matrix. In short, we see that the complexity of these expressions increases or decreases with additional ranks. Okay, and I'm going to spend 1 second here erasing some of this, if it'll let me. Yeah, my eraser is being very difficult. I think I can summarize nicely by simply saying, if we look at these expressions here, as we go from the top to the bottom, as we add new covariant ranks, we get new sums that are associated with the inputs, as well as new bases that are associated with the inputs. As we increase the contravariant rank, we get new summations that are associated with the output, as well as new bases that are associated with the output. So there is a one-to-one relationship between those characteristics of the equation as well as their contravariant and covariant ranks. Now, the second to last characteristic that we're going to talk about is how it reacts to change of basis. And this is probably one of the most important characteristics. A lot of times when you're working with a tensor, it's just going to be given to you, or it's going to be defined in some other manner. So you're not necessarily going to be defining its basis, defining its coordinate matrix or coordinate array. You're not going to be, let's say, generating in that manner. But one of the primary reasons why someone uses tensors is because they're trying to represent a system where change of basis or covariant change of basis will come into play. Whether that's because we need to account for change in perspective of the observer, or whether that's because we're using some sort of transformation in order to make the math easier. So let's take a look at this very important characteristic. How does the change of basis transformation change or react to additional or fewer covariant or contravariant ranks? So we begin by adding a single covariant rank, and then we'll look at the other. So essentially, this is our base case, and this is adding a single covariant rank. Now, I'm going to explain this expression briefly. However, if it is not very familiar to you, you may have to go back and take a look at the module on the bilinear map. Okay, so what we have here is a coordinate matrix for a rank 3 tensor that's defined in terms of 3 post-transform bases. 2 are associated with the inputs, 1 is associated with the output. How do we apply the transform or calculate this post-transform value from the pre-transform value? Here we have a similar coordinate matrix. Now obviously we're just looking at a single element. And now you see in its subscript, that's defined in terms of pre-transform bases, right? These bases do not match these bases up here. So this is the coordinate matrix we have before the transform. This is the coordinate matrix we have after the transform. Now in order to actually apply the transform, we need a number of transform matrices that corresponds to the number of bases, or the number of bases that are being transformed. For the time being, let's just assume that all the bases that exist are being transformed. And if they're not, we would just replace the transform matrices forward or backward with the identity matrix. Okay, so you see here that for the rank 3 tensor, this is a contravariant rank 1, covariant rank 2 tensor. And as such, we have two forward transform matrices associated with the inputs and one reverse transform matrix associated with the output. This is a clear relationship. 1, 2 corresponds to two inputs, covariant rank of 2. 1 corresponds to contravariant rank of 1 or 1 output. Now, if we increase the covariant rank, you can see here we're going to need to add an additional forward transform matrix that's going to be associated with the new input. We're going to need to add a new basis in there as well as in there. Right? The number of bases for the pre and post transform coordinate matrix should be the same, and then we're going to need an additional sum in order to facilitate the summation-based form. And that's what we have down here. Actually, I forgot to add an additional index. And you can see here, there's a mistake. This should be T, A, B, C. Right? I forgot to put the C in there. And then K. So in order to increase the covariant rank, what do? We add our new covariant index. We add our new basis set associated with, well, it's inverted, but the basis set associated with the new input. New summation. We have to add that additional index. New basis set, and one more transform matrix. So again, the number of transform matrices corresponds to the ranks. We have contravariant rank 1. We have covariant rank 3. We have one reverse or backward transform matrix associated with the only output. We have 3 forward transform matrices associated with the 3 inputs. All right, now we can extrapolate that a little bit further. I think the patterns are becoming more obvious. So if we go from original rank 3 and we increase the contravariant rank by 1, we need a new superscript. We need a new summation, which is defined in terms of the new output, which we call out2. We have a new backwards transform matrix. Again, I'm sorry, I didn't remember to put the new index in there. That needs a new index, a new superscript index. And we have our new basis. Okay, this is covariant rank 2, contravariant rank 2. And so we have 2 forward transform matrices and 2 backward transform matrices. It should be easy to realize when you're making a mistake, because let's say you tried, for this case, the covariant rank, contravariant rank 2 case, you tried to add a third forward transform matrix. Okay, well, where are you going to get that from? You don't have any more primal vectors to draw that from. Now, if you remember, right, each one of the basis sets is associated with a primal vector. And each one of the primal vectors has its associated transform matrix. So if we have covariant rank 2, contravariant rank 2, we can only have 2 plus 2, 4 transform matrices. We know that the transform matrices associated with the covariant and the contravariant components will be on opposite sides. One will be forward, one will be backward. So if you try to add a third forward transform matrix here, I would ask the question, where are you getting that from? Again, it's important to hammer home here that these transform matrices are specifically, they represent the transforms that are being applied to the primal basis sets associated with the inputs and the outputs. Okay, so now we decrease the covariant rank, and so we get rid of one of these indices. We get rid of one of the bases that's associated with the input, and we get rid of the forward transform matrix that's associated with the second input. And if we go down here, we do something analogous where we get rid of the only superscript index. We keep this guy and we get rid of this guy here. So this is contravariant rank 0, covariant rank 2. So we have 0 backwards transform matrices that are being used and 2 forward transform matrices. And then obviously you have to make sure the indices work out and the bases work out. So I'm moving a little bit faster as we go through this because the patterns that we see in the different characteristics also resemble each other. So we observed from that previous slide that an increase or decrease in covariant rank results in an increase or decrease in the number of forward transform coefficients associated with the basis input. Now, why do I call this a coefficient? Well, because this is a summation-based form, and so this is really not an entire matrix, right? This is just a single value from that. But for the purposes of discussion, I'm referring to these as an entire matrix, right? Because if we formulated this differently, we could represent it as a matrix. So the number of forward transform matrices or coefficients is associated with the covariant rank. And this makes sense because the covariant rank is associated with the number of inputs, and the number of inputs is associated with the number of inverted basis sets, and then so on and so on. Okay, if we increase or decrease the contravariant rank, we increase or decrease the number of backward transform coefficients or matrices, as well as the number of output-related sums. So we saw that the number of forward transformation coefficients or matrices correlates to the covariant rank of the tensor, and the number of backward transform coefficients or matrices correlates to the contravariant rank. The coordinate matrix basis will change as discussed previously. Okay, now I think this is the last characteristic we're going to discuss here, and that's the tensor product space. The tensor product space is a generalized representation of the space associated with our tensor, right? When we defined the primal vector, we talked about the primal space, and that's the space which contains all potential primal vectors that can be defined. When we define the dual vector, we define the dual space, and that's the combination or the set of all potential functional covectors, right, that could be applied to a given primal vector. And then we did something similar for the linear map as well as the bilinear map, except we call it the tensor product space. So the mapping associated with a tensor, right? Previously, we presented that there's really two variables or two characteristics that change. The number of input vectors, and that's going to match the covariant rank, and the number of output vectors, and that's going to match the contravariant rank, right? If we're looking at a general way of describing these tensors, and I think I've drawn this before, we have V out 1, vector product V out 2, tensor product ... is equal to some tensor times, again, assuming proper contracted ranks, VA, tensor product VB, tensor product ... Okay, so right, this represents the number of inputs, this represents the number of outputs, this is going to be correlated with our covariant rank, this is going to be correlated with our contravariant rank, and the tensor itself is going to have to react to those values, right? It's going to change its size, it's going to change its rank, it's going to change its form and structure. So higher covariant rank means we have more inputs. Higher contravariant rank means we're going to have more outputs, and you can see this, shown here and here. With regard to the addition and scaling rules, which is an important characteristic of any space, regardless of the covariant or contravariant rank, the addition and scaling rules associated with the tensor will pretty closely match those for any linear function and obey superposition. So if you look at the addition and scaling rules for a linear map, and especially if you compare that to the bilinear form, you can kind of easily see how those extrapolate out to higher rank tensors. Now, this requires the assumption that all the coordinate matrix elements and bases are constant and do not change with the inputs. Obviously, if we're dealing with a nonlinear system, then the superposition is not going to apply. And so here is a generalization of the tensor product space. And what you can see here, so we use these, the three dots to represent a general number of inputs. But The generalized mapping, we've already talked about that. Some number of inputs to some number of outputs where they're combined via the tensor product. And we have a pretty similar set of addition as well as scaling rules, which, like I said before, closely mirror the way that superposition is applied to any linear system. So, short conclusion, this marks the end of our tensors module. I may come back and add an additional module dealing with perhaps some preliminary calculus, like how to calculate a gradient array or a Jacobian matrix and how that fits into tensors. We may come back and deal with the tensor product or the contracted product, but for now, we're drawing this to a close. So the objective of this whole set of lectures was to introduce viewers to the topic of tensors, with a focus on the characteristics of lower rank tensors, vectors, covectors, linear maps, and then we extrapolated those to address generic higher rank tensors. Now, we've tried to address this topic by presenting tensors as pretty simple vector-covector pairs whose contravariant and covariant ranks have a governing effect on their form and behavior. And that's really what we've been talking about over the last 3 modules, is shedding some of those terms, right? Vector, covector, linear map, and learning how to describe tensors strictly in terms of their covariant and contravariant ranks. Now, hopefully we've achieved our goal by exploring the fundamental concepts behind those different tensor types, as well as representations of their primal, dual, and general tensor product spaces. So, I hope that by understanding how these elements interact and transform within a mathematical framework, we've laid the groundwork for you all to grasp more complex tensor operations and their applications. This foundational knowledge is crucial for appreciating the broader implications and uses of tensors in various fields, relativity, for physicists being one obvious one, for many engineers and computer scientists, that would be something like machine learning. But overall, especially for engineers, right, these tensors are vital because they're a powerful and flexible tool for modeling and solving complex problems in multiple dimensions, especially when you have to deal with the type of phenomena that may be represented through a covariant change of basis. Tensors are integral in various engineering disciplines, from structural analysis to fluid dynamics, electromagnetism. If we go outside of the engineering range, obviously, we have like stuff like relativity, and then engineering adjacent would be artificial intelligence and machine learning. And so by mastering tensors or learning more about tensors, engineers can enhance their ability to analyze intricate systems, predict complex behavior, design innovative solutions, and really just expand their horizon in terms of how they can represent values in an n-dimensional space. So thank you for listening to and watching these videos on tensors. I hope you found them very educational and maybe somewhat entertaining. And I'm still looking at what the next set of videos, the next set of lessons is going to be on, but I hope to be back with a new course set within the next couple weeks.